Okay, so welcome to this first part of examples in evolutionary dynamics. Today we're going to start with a very fascinating model that has been quite of a pinnacle of achievement in this field, which is called the Quasispecies model, and we're going to solve it for a particular simplification that is due to Suetina and Schuster. Okay, and so we're going to start with thinking a little bit more abstractly than usual. That imagine that we have, for example, in an urn, we have a set of n strings, right? So we have here n strings where the number of strings is fixed, right? So this is a fixed number of strings. Fixed number of strings. Okay, this is going already to induce some constraint on the problem. But now let's define a little bit more what do we mean by strings and what are they capable to do. In this case, they're going to be replicating strings. So consider a string S to be defined as follows, right? So S is going to have new, this is the letter new binary numbers here. So in other words, each of these new variables here are going to pick up values from 0 and 1, and I, which is basically the label for all of these variables here, is going to go from, well, is going to go from 1 to new. In other words, we could say that new is the string bit length, right? We're going to have n of such strings that are sitting in this urn, right? And the point is that these strings are going to be replicating and they're going to be making mistakes at this sort of replication. Notice that from the notation that we have already established in this course, what we could say is that this sort of object here belongs to the hypercube, okay, of length mu, corresponding length mu. Again, this is defined as this set. Remember also that the total number of possible strings that exists for this system is a very large number indeed, right? As soon as we go to something like 10 bits, we will have 2 to the 10 possible strings in the system. That's a really large number. As you increase the value of the bit string or the length of a bit string, this is going to become even more and more large. And it seems to be a bit untreatable, but now we're going to introduce something that is very fundamental for this problem, which is a single peaked landscape that allows us to make some simplifications and try to move forward in this problem. Okay, so a little bit more definitions before we go on. Now we're going to define something that it's called a single peak fitness landscape. Okay, so how do we do that? Well, in this case, this fitness landscape is going to be introduced as a function, right? And it's going to be a function of this, that picks elements of this set and puts them into the reals. So in other words, we will have something like this. This is a function, f for fitness function, that takes elements from the strings, right? And in this case, there's going to be only 2 values that this is mapped onto. Okay, so how do we map this? Well, we take a given string, right? And then we will assign either 2 values. So the fitness function of that string will give us either f1, if and only if this string is what we'll now call the master sequence. And it's going to be f2 if it's not the master sequence. Okay, so here we have a definition, which is master sequence, which this definition basically stems from how we have defined this fitness landscape. And the master sequence, we just name it S sub m, right? For example, without loss of generality, we could say that this master sequence is the one that contains all zeros in the bit string. But how do we picture this very there's something else I missed here. Importantly, we will set f1 to be larger than f2. That's the single peak issue with this landscape, right? In fact, what we are saying here is that there's going to be one string that is going to be more fit than all of the other strings. How do we depict this? How do we make a depiction of this? Well, it's pretty straightforward if we think about, for example, let me write here using two colors. Here we're going to have some of the non-master sequence fitnesses value. So this will be F2, right? And then at some point, and this is kind of a projection of this highly dimensional space, right? At some point, we have our master sequence, right? Here, this is the master sequence, and these are sequences that I'm going to denote as mutant sequences. So basically, a mutant sequence is any sequence that is different from the master sequence. That's how we define a mutant sequence, and we call it S sub little m. Okay? Of course, here the value of the fitness will be F1, and all we have said through this condition is that this has a larger fitness value. Again, what does fitness mean when we're talking about evolutionary dynamics? And here's where we start making some of these approximations for this problem, right? Fitness relates to the capacity to replicate, so to the rate of replication. As a matter of fact, in this problem, we will take it to be exactly that. So the fact that there's a sequence that we call a master sequence that has a higher fitness value only means that it is better at replicating than all of the rest, namely all of the mutant sequences. Okay, so if we wanted to take all of these ideas and now compress it into a system of ordinary differential equations, how could we go about doing that? Well, first off, let us denote x sub m as the concentration of sequences of master sequences. So, namely, if you want, x sub m will be defined as the number of master sequences that are in the urn divided by n, which is the total number of possible strings. On the other hand, we will define x sub m, little m here, by the number of mutant sequences divided by n. So now with these two definitions in mind, we can set out to write down an ordinary differential equation model that will map these different aspects that we have been talking about. So let us consider these two systems, these two sectors of population. First off, what we say is that this F1 has to do with replication, right? So there's going to be something here that will be connected to F1, right? And there's going to be something here that will be connected to F2. Okay, let's move farther than that. Also, we know that there's going to be some competition due to the fact that while these two are replicating, they are replicating inside a fixed sized urn. In other words, because the total number of strings must be fixed, we will have to induce some phi outflow function that corresponds to a constant population constraint that we will see later. But in fact, well, we can just directly see here that this has to be held because the total number of sum of the master sequences plus the mutant sequences divided by n, it must be 1, right, all along the problem. But we're not there yet. There's something that's fundamental that occurs in evolutionary dynamics we haven't spoken yet about that will complete this picture, which is mutation. Okay, so now let us think a little bit more about what this means. So a sequence, namely a master sequence, for example, it'll be a set of bits, right? And when this is replicating, basically it'll leave the parent string and then it'll generate a new one. So this could be exactly the same. For example, imagine that this is all ones. This leaves an all ones sequence, but maybe there is a mistake happening here, right? If there's a mistake happening here, then this sequence will no longer be exactly the same copy as its parent sequence. In this case, a mutation has occurred. Now, what we will say for the moment is that mutations occur with probability mu. In other words, what we're saying is that any given string, when replicating, it'll lose its information in whichever way, either by changing 1 bit, 2 bits, or many bits, at this probability. Great, so what does this imply for our system here where we had the master sequences and all of the mutant sequences? Well, clearly, when the master sequence is replicated, there's two things that can happen. It actually generates the same two master sequences, namely this is the parent one, and then it generates another master sequence. So far so good. You can do this at rate f sub 1, and if you think about it, it must be at rate f sub 1 times 1 minus the probability that I fail at this. There's another possibility, right? That the master sequences replicate and it gives you its parent, but then it gives a mutant because it has failed at replicating properly. What is the rate at which this happens? Well, clearly this happens at the rate of replication for the master sequences times the probability that it made a mistake. So this is very important, and now we need to map this idea into our dynamical system, which is not completed yet. But from what I've just said, it seems pretty clear that what we have to tweak our model with is these two elements, right? So when I'm replicating the master sequence, I need to add here this extra bit, right? And there's something else that can happen. In fact, while replicating master sequences, there's the chance that I actually feed onto the mutant set of, or the mutant pool of sequences, right? And that comes with this, following the same argument that I've just explained. Great, and now somebody could say, wow, but could the opposite also happen, right? Could there be mutant sequences that mutate such that they become the master sequence? And of course this could happen, but it's extremely unlikely. And you can think about why is this extremely unlikely, right? So consider this argument, right? So the probability that I go from a mutant into a master, it has to be of the order of 1 over 2 to the mu, right? In general, because given any single string, I don't know, a bunch of zeros and ones there, like the chance that the mutation goes exactly to one single bit string that corresponds to the master sequence, for example, here I've considered it to be all ones, right? This doesn't really matter. I mean, you can take any values here because there was nothing that that was corresponded to this information. So anyway, this is just a convention, but I want you to imagine how unlikely it is that any given sequence of zeros and ones will mutate to specifically go to all ones. In this case, because this is so small, we can consider it negligible, right? And when we neglect this sort of back mutation, what we're saying is that virtually there is no back mutation. Okay? So if there's no back mutation possible, there will be no flow from the pool or the populational pool of mutants back onto the master sequence. And this, with this hypothesis here, we are now set out to solve the dynamics of this problem and see what will happen for the few parameters that we have here. Remember, the fitness landscape gave us two real values, f1 and f2, right? f1 for the replication rate for the master sequence, f2 for the replication rate of the mutants, and the mutation rate, which we will talk about in depth and more in the next minutes. Great. So far we have turned and crunched down this very interesting model into what we now can manipulate, which is a dynamical system. Okay, we have two populational sectors. They have a constant population constraint, as we have discussed before, which is that the sum of the two concentrations from both master sequence and the set of mutants must equal 1, right? And this will be captured by this outflow, which we have to compute now. But now, with all of this in mind, or taking also into account the mutation aspect, the mutational aspect of the master sequence into the mutant pool, we can write two differential equations, one for the concentration of master sequences in the urn, and another one for mutant sequences in the urn, right? And we can proceed as usual. So first off, we see that master sequences replicate themselves, but they may commit mistakes, so they don't replicate perfectly. In fact, sometimes this factor here is called the quality of replication, right? So this is going to go along these lines. But on the other hand, there is an outflow due to the fact that these two populations are competing, right? In the sense that they have to occupy the same number of, the same size of the urn, right? And remember, this is always done by using an outflow function that we need to compute externally. This function will depend on both variables, master sequence concentration and the mutant one. Again, now we look for the mutant, and as we have discussed before, because we have included all of the possible mutants into this particular populational sector, we also could argue that there would be no back mutation towards the master sequence. Again, remember, because there's only one single master sequence and the rest are mutants. This is in virtue of how we defined our single-picked fitness landscape. Therefore, all the replication rate for mutants will basically generate more mutants, right? Remember, this is F2. Also, do recall that F1 is larger than F2. We need to remember that from our definition of our landscape. But there's also an interesting aspect here, which is that the population of master sequences, when they commit a mistake, when they make mistakes, there is mutation, they basically start feeding the population of mutants, right? And therefore, there's going to be a plus sign here. The replication rate of a master sequence times the probability that they make a mistake times the concentration of master sequence. So there's this coupling here now between these two variables. Finally, there's also the outflow, right? Which also couples all of the system together. So this is our system of ordinary differential equations, and we shall now proceed as usual, right? Remember that because we have such a constant population constraint, we can always say that the derivative of these two must be 0, right? But we can use the distributive property of the derivative, and we now know that this plus this shall altogether be 0. Remember, we can always use that. In this case, we can always use that the master sequence concentration plus the mutant sequence concentration will be 1. Therefore, for example, here when I'm adding these two, I'm going to be only left with phi, right? If one does this calculation rather quickly, we see that also the mutation rate will cancel. The mutation rate term with x sub m, large M, will cancel, and we'll be left with this. Right? Because this is 0, just as we have just discussed. Then we have that this outflow corresponds to nothing else but this, which, if we think about these concentrations, the master sequence concentrations and the mutant sequence concentrations, as probabilities, which they could be thought of because precisely they are normalized to 1, then we could think that this is just the average value of the fitness function, right? And this result is not the first time that we see. We have seen this before when we studied replicator systems, and it's kind of a general thing that can happen for replicator systems, right? For simple replicator systems, we shall always see something like that for the outflow function. Great. With this in mind, we can now reduce, and that's the beauty of this, we can now reduce these two ordinary differential equations into a single one. And because we are interested in understanding how this urn will be filled with either master sequences or mutant sequences, makes logical sense that we take master sequence concentration as the variable of interest. Okay, let's do so, and actually we can just pick this equation again, right? So I take this equation if you want, and I come down here, and I rewrite it with all of the information that we have just derived, right? So let us rewrite it here. And if you notice this, I'm gonna be doing it, yeah, like that. There's gonna be a bunch of terms here. Notice here I'm just substituting this phi function, right? notice that this actually 1 minus xm, it's coming from the fact that I have an xm here, right? And what I want to do is substitute using the constant population constraint. Well, I'll take this equation, I come back here, and now I can just figure out all the roots because I can take common factors, etc., etc. This is an exercise that we should be able to do without much of a burden, and we are going to end up with something that looks like this. I'm sorry, this is F2, obviously, here, like that. And great. So now we have reduced all of these ordinary differential equations, the two of the ordinary differential equations into one, right? And this, we observe, it has two roots, and this is begging us to start performing some fixed point analysis, right? So obviously there's going to be two fixed points here by looking at the roots of this polynomial. One fixed point I'm going to call xm naught up here is basically 0, right? So if I have a 0 here, we know that the derivative is going to be 0, and therefore this is a candidate for a fixed point. It is a fixed point. On the other hand, I also have another fixed point from this linear equation here, right? Which is basically xm divided by, 1 minus mu minus f2 over f1 divided by this prefactor here of xm. Altogether, this gives this expression. Right? Great. So it's going to be interesting from here onwards to define something that already succinctly we are calling it the critical mutation rate. And it's going to be given by this expression. Notice that this is sitting here at the denominator. In fact, I could rewrite this as 1 minus mu over critical mu. We need to work a little bit more here. We need to do the stability analysis. Right? But we have done this many, many times, and now we can do it just with ocular inspection, right? So we see that it doesn't make sense when we have mu larger than mu critical to have xm1 be a stable point. I mean, if this happened, this model would be a little bit ill-defined, right? Because we would start going into the negative values for a concentration, which makes no sense, right? Therefore, if one does this properly, using all of what we taught you about lambdas or the Lyapunov coefficients, etc., or if you wanted to go and study the potential function of this system, then you will see this happening, right? But here we're going to work a little bit quicker using our intuition and the fact that we have done already many, many of such problems. So initially we see that if mu is larger than mu critical, this thing here makes no sense because it goes into the negatives, but that actually is self-resolved by the mathematics, and it gives us that it's going to be the trivial fixed point, namely the 0, that's going to be stable. Right? Therefore, what we'll have here is that this is going to be non-physical. Actually, our non-trivial solution will be sitting on the non-physical, on the negative concentrations, and it's only going to be the fixed point 0 that is going to be an attractor, right? On the other hand, when we are at the opposite situation, now this will give rise to a suitable value, right? It's going to be a value between 0 and 1, and in fact, that's when the stability exchanges, right? And it's the non-trivial fixed point that is stable. Again, we can depict this as here. This part here is the non-physical part. This is xm0, which is 0. Again, this is xm0, which is 0. And now we have a fixed point here, which is an attractor, so it's a stable, which is xm1, right? Great. We're going to take this intuition now, and we're going to write and draw a phase diagram of the two characteristical states. And we're going to discuss a little bit further what does this entail when we are thinking about this system as strings that are being replicated. Okay, so we need to bear in mind that there's going to be two possible fixed point states, depending on the parameter mu, which is noticeably is the mutation rate, right, or the mutation probability, more succinctly. Okay, and notice also that what's happening here is that if the mutation rate is sufficiently large, the mutation probability is sufficiently large, then I'm going to have no master sequence left in the system. So the system will be all a bunch of mutants. Right? Whereas if the mutation rate is smaller than some critical value, what I have is that there's still a bunch of master sequence replicating around in the system in the stationary regime. Okay, which is what we are basically studying when we study the fixed point. Okay, so, well, we erase this and then we will continue. Great, so now we have found what are the fixed points and their corresponding stability. What we can do next is to plot a phase diagram here, where we're going to use naturally the mutation probability here as our driving parameter, right? And in the y-axis here, what I want to plot is what's the stable fixed point in each case. Notice that for mu, there's going to be a critical mu over here, right? And for mu less than this critical mu, what we have here is that there is master sequence, there is a non-zero value or non-zero concentration of master sequences in our urn, right? And it goes down linearly with this probability of mutation mu, right? So it goes down linearly like that until it hits exactly 0, right? Which is precisely at the critical point, right? From this critical point onwards, what we have is a phase where there's only there's only mutants in the urn, and there's 0 master sequences left in the urn in stationarity, right? So this we can depict like that, right? So here we're going to have two regimes basically. Okay, the slope of this is 1 over the critical value, a mutational critical value. And here we have master sequence present, and here we have only mutants, okay? Great. What can we get out of this? What can we interpret out of this problem, right? So interestingly, what happens here is that if you have a large mutational rate, there is a transition, there is a phase transition between staying present there as a master sequence and losing your presence and basically become completely extinct. This is what theoretical biologists dubbed the error catastrophe, or sometimes also called the error threshold. Why is this important to us? Why is this interesting? Well, if we now look at what happened for RNA viruses, which we're going to explain a little bit more, we find that, that most biological systems, or some biological systems, more succinctly, will be poised exactly around this critical point, right? How can we make sense of this, and how can we even go out and measure this in nature? Well, remember that we're talking about strings here, strings that are being replicated, right? And we used the following metaphor. So there would be a string here, right, which is basically of size mu. For example, here, if I make this 8, here mu equals 8. Here I'll have some zeros and ones, right? And what's happening here is that there would be replication of such strings. And when they were replicating, as we said before, there could be mistakes. These mistakes could happen for a particular bit. And that would basically move that string from one, if you want, one species to another one. But we have compacted these two between master and mutants. Now, let us then distinguish two probabilities here. This is the probability of mutation. In however many bits you can imagine mutating after a replication event, then that's the probability that captures this mutation. But we could also go a little bit more fine-tuned, and we could say, okay, what's the probability of mutation per bit? And that's what we are calling here mu sub b. Can we relate these two? Can we relate the probability of mutating a string after a replication event and the probability of having one bit flipped, either from 1 to 0 or 0 to 1, it doesn't matter? Well, the answer is yes, we can do that, and we could think of this a little bit on the following lines. Like, consider, for example, the probability that there is no mutation. So basically the probability that a given S string, whatever it is going to give rise to two S strings that are exactly the same. How do we resolve this probability? Using the probability of single bit mutation. Well, for this to happen, if we think about it, what we shall see is that there is no mutation for the first bit. So basically, when this is replicating, the first bit that the replicated sequence should be 1. The next one should be 0. The next one should be 1, and so on and so forth. Therefore, each of those bits should not make a mistake. Because mu sub b is the probability of making a mistake per single bit, then we have to multiply this probability a total number of, in this case would be 8 times, but in general it would be nu times, right? Remember, this is the length of this string bit, or of this bit string. Great, so this is the probability that I replicate properly, right? But remember, we defined mu to be the probability that I do not replicate properly. And I could make mistakes wherever, right? In either 1 bit, 2 bits, or many bits. So altogether, what we have to think about, and we have seen this kind of argument before also when we are using reliability theory, what we have to think about is that the mu is going to be just a complementary probability of this one over here. In other words, mu should be 1 minus the probability that everything goes well. Okay? Great. Now we can work a little bit further with mu, right? We can, for example, use this approximation. If mu should be the probability of mutating a bit, it's rather small, right? And we are raising this to the power of mu. We notice that this is going to be equal to this. 1 over mu sub b, and all of this to the power of mu times mu sub b. That's completely fine. There's nothing strange here, except that why are you doing this? Well, if you think about this, we have seen this before in mathematics when we're talking about the exponential function. There's a minus sign here, so basically this is going to be e to the minus 1, which when it's raised to the power of mu times mu sub b, the probability of single bit mutation, this is going to give rise to this term. Actually, this is an approximation if you want, and that only works for very small values of single bit mutation. Great. So now we take this bit of math here, and now we go back to what our result was concerning the error threshold or the error catastrophe. Remember, the error catastrophe happened for when our general mutation rate had a particular critical value. If we go back to our single peaked landscape, this corresponded to this specific value, right? How can we relate this now to the characteristic, or if you want, the critical single bit mutation rate, or single bit mutation probability, more correctly said? Well, we have that this mu actually has this expression here, and this expression we just said that it can be approximated by this other one, right? Just I'm plugging this into here. Great. So for the specific case of the critical mutation probability, what we have is this should be hold. Right? Of course, this is approximated, but from here on, we are just taking it to be exact. Great. So this gives rise to the following value for the critical mutation probability for a single bit, so for a single letter flip, if you want. And we can do this rather quickly. I leave you this as an exercise, but this basically gives rise to this expression. Notice here that when you algebraically manipulate this, there's going to be some signs. You have to be careful with that, the minus signs here. And now this makes sense because f1 is larger than f2. Remember, this is part of our definition of our single peaked fitness landscape, and therefore all of this is going to be positive. But what's important about this, what really matters, is that this specific case, this particular situation is giving us some, if you want, some scaling law for the critical mutation probability per bit and the size, right? The size of our string. And this is very interesting because this is the kind of thing that we can study and we can experimentally probe, right? As a matter of fact, when scientists went on and studied RNA viruses, and they, for example, estimated what, using sequencing, right, you could estimate what's the mutational probability that for a single letter of RNA viruses to change, right? So we would have an estimation of this, but on the other hand, from the same sequencing data, we could obtain what's the length of this information for each of these viruses. So what's the length of the RNA strand, right, for all of these viruses. And then people could plot, for example, the logarithm, natural logarithm of this, well, let's call it experimental single letter mutational rate. And here we can plot the logarithm of the length, also experimentally measured, the length of these RNA viruses. Oh. Great, and people started doing that, and they saw that they followed a trend. You could find this in different sources, right? But the trend basically said that this was following in log-log scale, it was following a line that was going downhill like this with a slope that was very close to -1. So why is this interesting? Well, if you think about what we have done here, if you now take the logarithm here on our, if you want, theoretical expression for the critical mutation rate, you take the logarithm here, you take the logarithm here, you'll see what happens here is this log mu is going to be proportional to minus log nu, right? Because the logarithm of 1 over nu is going to be minus logarithm of nu. And that trend is exactly what we see when we go to the experimental data for RNA viruses. Okay, so what is this teaching us? What kind of evolutionary process is actually making RNA viruses, instead of being all happy and maintaining themselves here at the master sequence level? Remember, this means that inside this pool, inside this populational pool, you are always present and therefore you can keep on surviving. That seems rather a good idea from an evolutionary standpoint. But if you go over here, you basically will lose your information because your mutation rate is so high that very soon you lose the kind of information that allowed you to be a faster replicator, right? So you will become a mutant, which, remember, has a lower replication rate because F2 was smaller than F1. Why would viruses go all the way there? Of course, we understand that viruses don't want to be beyond the error catastrophe, right? They should want to have some useful information to be kept onwards on the evolutionary process. Well, the answer is that viruses are well, there's a lot of interesting dynamics with viruses, but more importantly, viruses have to compete totally with their host immune systems. Therefore, they need to innovate continuously. They need to vary very rapidly. This basically pushes their mutational rate to their maxima. And its basic barrier here is the error threshold. So if you want, here we could say this is the error zone, where basically you are no longer you can no longer produce meaningful information over the replicative process because your mutational rate is too high, right? And here you have the master sequence, but because you can be targeted by the immune system in general, then you need to push for higher variability. And there's this tug of war, evolutionary speaking, between these two forces, right, that poise our system right at the edge of criticality. This, as a matter of fact, has also been quite an interesting issue in evolutionary dynamics, and people have dubbed this the idea that biological systems may be poised at criticality in different ways, and we shall explore this further in these lectures. But this is a very interesting and important example, and it falls under these assumptions, which is called the quasi-species model. And just to finish up, sometimes we say that viruses are quasi-species. Why? Because the fact that they are sitting right here at the edge of criticality imbues in them some sort of notion that they are not exactly a species that it's very well defined by its RNA sequence, but rather by a cloud of different RNA sequences that are just at the edge of criticality here, oscillating between being completely useless, being completely catastrophically bound and therefore not able to replicate, and being right at the edge of the capacity to keep on replicating successfully, right? Great, so we have already established what a quasi-species is and how its dynamics work. We have done this using ordinary differential equations. It's also important now to mention as well that this model was introduced back in the 70s, and it was only recently, in the last few decades, that all the sequencing processes has been sufficiently technologically advanced in order to gather all the data that I've just explained. So it's a remarkable example of how theory in biology also can go very far before the experiments can actually prove that hypothesis, okay? Great. In this example now, we are going to explore the exact same problem, but from a completely different standpoint. That I wish that this inspired you to understand other many biological systems and gives you some extra elements in your toolkit in order to explore complex systems. Great. So now, again, we are talking about the quasi-species model, and here we have the following depiction. Imagine that we had a master sequence, our beloved master sequence, and there's three possible things that can happen to it as it replicates and as time moves onwards in this evolutionary process. The first thing that could happen is that it degrades, right? So it basically disappears from the system. How could this even happen? Well, from our system before, this is not the same instance, but we can trace parallels. In our system before, in the problem before, we had that there was an urn, right? And that in that urn, you could be flown away through the outflow that was induced from the constant population constraint. That would be what is equivalent for this specific process that we are introducing here as something that could happen to our master sequence, okay? So there's all these parallels that one can trace, but here we're going to basically, if you notice, we're going to dissect the problem in a completely different way. So keep on with me for a while and you'll see how this becomes rather interesting in a second. First off then, we had this degradation process. The master sequence disappears. Another thing that could happen is that the master sequence effectively replicates, and it does so perfectly. In other words, if the sequence that corresponded to the master sequence was all ones, in this binary representation that we've used, then there's going to be a parent and a daughter sequence, and both are going to be exactly all one. So this is a perfect replication. Okay. And then on the other hand, we could have that one of the daughter string is going to be a mutant, and the master sequence parent, it basically keeps the same. So there's these three different possible outcomes that occur at a given iteration of this evolutionary process. And this will see that this is exactly the same problem as the quasi-species problem that we have studied before. Now we need some definitions, right? So remember that before we had mu sub b was the probability of mutation per bit. Okay, allow me just for also I introduce some more notation. Allow me to call Q, which sometimes is called this for quality, right? To be basically the complementary or the opposite probability, namely the probability that there is no mutation for that single bit. So we call it quality per bit. Again, all of this is per single bit. Okay, so we have this definition here. We can also define another probability that it will play a role in each of these replication events, or in each of these iteration events, which we are going to call W, okay? And this is going to be the probability of no degradation. Notice here that I'm saying the probability of no degradation. Of course, we can use either W's, mu's, whatever we want, but we need to introduce some of these probabilities in order to proceed now with what this system, which is going to be an iterative system, is going to be looking like. As soon as I start putting some master sequence in my space here, and it goes on replicating, what we expect to happen. That's our question here. Great. So now for these three different possibilities, again, degradation, perfect replication, and mutation, we shall derive, using these parameters that I introduced, we shall derive the different probabilities that each of these happen at any iteration. So we're going to call P1 the probability that degradation happens, and if we have denoted W to be the probability that there's no degradation, then trivially this is going to be 1 minus W. So that's the probability that degradation does happen in any such iteration. What's the probability that actually there is a perfect replication? Well, first off, there must be no degradation, right? Because if the degradation happens, we are stuck with this process, and then there's no further questions. So first off, we need W here, so that we are sure that no degradation will occur. And then we need to think about the quality of the replication. So what's the probability, remind ourselves, what's the probability that I replicate properly? Well, I need all of the string, right, to be correctly replicating. If the string is of length nu, if the string is of length nu, the probability that all of its bits will replicate correctly is going to be q to the nu. And that's what gives rise to the probability of this three-sided process that the second sub-process happens, right? So there's a perfect replication. That's the probability for the second process to occur. If you think from before, this is exactly W, 1 minus the probability of a single bit mutation to the power of nu, right? We've used this before on a completely different approach, but still we're talking about something that it's going to be eventually looking at the same problem, right? So this is equivalent. Finally, we want to know what's the probability that I do not degrade, then I need to include W here, but also the probability that I actually mutate in the system. So if I mutate, I only need to basically change any of the strings, any of the bits in my string, right? Remember, q to the power of nu is the probability that none of the bits in my string do mutate. Therefore, 1 minus q to the power of nu is going to be the probability that any of the strings do, of the bits do mutate, either 1, 2, or whatever. So that's my term here that I have to include, right? Notice that this is not going to be so easy to write, because we have to write 1 minus mu sub b to the power of nu, and so on. So we are going to just, for now, ignore this part. Great. So we have these three probabilities here, and now we want to basically do an exercise which is rather simple-minded, which is just start drawing what you should be looking at when you put a master sequence in that system and start looking at how it's going to be branching out. Well, let's do it. Let's say this is my initial time, right here. I'm going to do, I don't know, a couple of experiments, right? So a master sequence will be denoted like this, right? A mutant sequence will be denoted like this, and then when it basically is degraded, I use this, which could be corresponding to halt, right? So stop here. There's not going to be more replication. How does this look when time increases this way, right? Iteration time goes one by one, following up this way. Well, first I could just draw something very simple. So we start with a master sequence here, right? And well, it starts with the process number 3. So here we have process number 3. I produce a mutant, and I produce another master sequence here. The mutant, the mutant will keep producing more mutants, but as we have explored before, and we're using the same idea here, there will be no back mutation. The mutants cannot generate any more master sequence. So whatever happens here, we are no longer interested in. Okay? Now, what happens next? Well, we have still a master sequence here. Suppose that now it replicates properly. Great. So it replicated properly. But now maybe here, this one degrades. So this stops. And maybe this also do degrade. So this has stopped. This was quite unlucky. But then this system only went up to here. Great. So this will happen given some Q value and some W value, right? And we could keep on doing some of these exercises or experiments, right? So for example, here, let me draw it a little bit more here, right? Here I could have good quality replication, another good quality replication, right? And here also more good quality replication. But then here this extincts. But then here this also extincts. And then here we have a mutant and a non-mutant. Here we have two good quality replicators. And here this extincts. But then here we have also two good quality replications, and so on and so forth, right? Suppose this extincts, this becomes mutant, and we should keep moving all along. So this is generating, let's say, this could go on until at some point it will stop. So basically this is generating branching processes, right, that will go all the way up until some point. Great. Can we study these branching processes in a minimal way, maybe using the probabilities that we have developed over here? Well, the answer is yes, but there's going to be something here that I need to point out, which is that we're going to be neglecting the fact that all of these branching processes eventually will stop, right? Why is this? Because they have what's called an absorbing point. Eventually, even if it takes forever because the probabilities are so tuned such that these systems go on and on and on for a long time, eventually all of them will eventually degrade. And this is called an absorbing point. So there is an absorbing point because there is degradation. But for the purpose of this exercise, for the purpose of what we're trying to analyze, we're going to ignore it. Okay? So we're going to ignore it for the purpose of this example, but I wanted to point out that this is going to happen, right? So eventually these trees are going to finish somewhere. And this is because, again, we had a degradation element. Great. So ignoring this bit of important information for a second, how can we actually probe the system? Can we say something about, given the values of Q and W as parameters of my system, and also notice also nu, the length of the strings that are being replicated here, can I actually say something about how I should expect this to grow? And the answer is yes. But let us think of the following. So going back to the three cases, right? So here, the first case, I have a master sequence, and it goes to nothing. Can I ask, so here we had a number of master sequences, which was 1, and then after that, I get a number. So n sub 1 is going to be the number, right here, is the number of master sequences after the ith process. So in the first process, which was degradation, how many master sequences do I get after I move onwards in this iteration time? Well, I get 0, right? So this is actual degradation. I have a master sequence, and after that process, I get no more master sequences. Great. Let's see what happens in the perfect replication. In the perfect replication, we had that I had 1 master sequence, and after this iterative process, I get 2. Interesting. I don't know where we're going with this, but let's move on. So here we had our last process. In our last process, we got 1. We just maybe do this a little bit better. Yeah. So here we have 1 mutant, but we are still left with 1 master. So after the third process occurs, I have still 1 master sequence to keep pulling out from, right? So this master sequence could still be replicating. Okay, so I've written these 3 variables here, which, okay, makes sense if we pose the problem like that, but this is the critical thinking here. So if I want to know what's the average, this is how we denote average, so in mathematics or in physics in general. Basically, what's the average number of master sequences that I shall expect from any given iteration process? So this is what we should read when we write this. What's the average, given our definition, what's the average number of master sequences that I should expect after each of these iteration events, right? Where I can either degrade, replicate properly, or replicate with a mutant. Well, how do we compute this average? Well, we know that with probability p sub 1, all right, you're going to end up having n sub 1 master sequences, which corresponds to the process 1. Oh, remember this is actually 0, so you end up having 0 master sequences. But okay, this is only weighted, right, pondered by this probability sub 1. Okay, what happens with probability sub 2? Well, with probability sub 2, right, I actually end up with 2 master sequences, right? So this kind of weighs this out somehow. Let's see where we can go with this. Finally, of course, for probability 3, I end up having, well, still just 1 master sequence. Okay, right, so this really is looking now good for a candidate expression for the average number of master sequences that are left after an iteration. This is rather simple maths, but it takes a little bit of thinking of why this is correct. Great. Now that we have all of these in mind, we have established what n meant, right? And we also have computed before P1, P2, and P3. Notice that because this is going to be 0, I can just get rid of this one, thanks to the fact that this is 0. Not because the probability of degradation doesn't happen, it's because when I degrade, there's no master sequence left. What about here? Well, here I have a 2, here I have a 1. I need to basically do this calculation. 2 times P2 plus P3. And we have computed this before, right? I'm going to write it down here. We computed this before, and it's basically this times 2. Well, if you want, 2 times this. All right. Plus W1 minus Q to the power nu. All right, this was P3. I think I'm saying this correctly, yes. In fact, when we notice that here there's 2 times W Q to the nu, and here there's 1 W Q to the nu, but with a minus sign, so we're going to be left with the following. W1 plus Q to the nu. That's the average number of master sequences that are left after any iteration process. So this is what we need to think about now. This is the average number of master sequences that are left after each of the iteration processes that are happening in this branching sort of way. And here's where we need to, again, use critical thinking to understand what's going to separate a process with any of these variables that keeps on going almost forever. We know that it's not going to be forever because there's the absorption point, but we ignore that and we think of it in an average way, right? In average, what's the condition that we need to impose so that for any given set of parameters, this keeps on growing and growing and growing? And what's the condition that we need to impose here in this expression so that for this set of parameters, this is going to be stopping at some finite time? If we think deeply about this, the condition is the following. The critical number of leftover master sequences must be 1. Why? Well, let's think about this. Suppose that the average number of leftover sequences is smaller than 1. This means that in any of these replication processes, in average, I'm leaving less and less and less numbers of master sequences. So very quickly, this will die out. In the other hand, if I actually have that the average number of master sequences left after each iteration is larger than 1, this means that on average, I shall be increasing all the branches of this process, right? Therefore, we have established that this is our critical average number of leftover master sequences. Great, because this now establishes a condition. For example, we can relate the critical value of the quality of the replication of each of the bits inside my string with this particular condition through the expression that I have over here. As a matter of fact, let's do it. And I know that this is going to be 1. That's assuming that we have the critical value for the leftover number, average number of master sequences, 1 equals W, 1 plus Q critical to the power of nu. Great. We can now actually use the fact, and we have mentioned it before, that Q was nothing but 1 minus mu, the mutational probability for a single bit, right? We have used this as a definition. Let's consider the critical mutational problem of a mutational probability for a bit. And now I leave this as an exercise to you, but from this expression, using this that we have established before, you can derive the following equality, right? So this is going to be 1 over the size of the string, again, times a logarithm of, times the logarithm of, well, this is going to be a bit more cumbersome, but it's going to be 1 over 1 minus 1 over W, okay? Which you can turn to W divided by W minus 1, okay? Anyway, you can prove this, but what's important about this is, again, we get this 1 over mu behavior, right? So we also always going to get, for this same approximation, we are getting that there's going to be a critical value for mutational probability for each bit that is going to scale like 1 over the length of the string, of the bit string. Great. Let me erase here and I'll explain something else about this, and we'll leave it here. Before we go on, let me say that in the previous blackboard there was a mistake. There was a -1 missing in the numerator, otherwise it wouldn't have made sense, so some of you might have spotted this already. You can rewrite this as the following, and that's actually more accurate or more elegant if you want. The point still being that the critical mutational probability for bit, it's the same expression as for what we have derived before. Noticeably, there's 2 words here that we have been kind of using willy-nilly, and I want to make a bit of emphasis on this. So there's the idea of a branching process. This is what we have been exploring. Again, using the quasi-species example as an excuse, we have reduced this to a branching process and established a very few rules that allowed me to compute, again, what would be the critical point, below which I will have no master sequences left, and above which I still will keep seeing master sequences on and on into the system. So branching processes are widely used in a variety of areas of research, but of course they play a big role in biology or in theoretical biology too, right? Another issue that I haven't mentioned, but it's important to study, that the transition that we saw from master sequence present and no master sequence present can be tailored to something that it's called a percolation point. Percolation point in this case for this particular branching process, right? And I want to just mention very briefly a very nice example that is widely used in simple models of contagion, right? Which stems from an idea, just called a Bethe lattice. Okay, so you can imagine as follows. So I have some node here, and these nodes connect to, in this case, we'll use that it connects to 3 neighbors. So in this case, we say that the Bethe lattice is with neighboring coefficient 3. Now this connects with 3 other nodes, right? And the idea here is there's going to be some flow, some outwards flow. Again, this is going to look like a branching process, but in this case, it's going to be a branching process like radially, stemming out from this central node, right? And this is going to be all keeping connected 3 nodes at a time, right? I'm going to draw it just a little bit more because it's very pretty. right? And this can go on, and this is used in many different areas of research where we have something that can be equivalent, if you want, to a contagion process, right? Or some process that basically, here's the idea, that could percolate across a given network. This is a very simple network that's very regular, right? But it's characterized this way. So here, for example, we would have an initial activity point that it propagates throughout these branches, right? And it could keep on propagating, and maybe there is some cutoff here. And a lot of times what we want to understand is where do I have to cut the system so that maybe if we are interested in this contagion process not to propagate, well, then we want to cut off the, some particular nodes that will be basically avoiding large branchings, right? In fact, it's very easy to compute the percolation point for this specific example, because if we think of this as some sort of activity propagation, right? We could also use time in a discrete way. So we have time 1, 2, 3, etc. Again, this, as we have done in the previous example, time goes here unit by unit. So it's a discrete time process. And very simply, we could say, okay, so if the probability that I keep on propagating this signal over here, whatever it is, it's p. So each of these neighbors will propagate with p. Now forget about the initial set of neighbors and think about, for example, here I get the signal, right? And then I might propagate towards that neighbor, I might propagate towards that neighbor with probability p in each case, right? So if I denote the activity at time t, right? And I'm going to do this rather quickly, but I want you to think about this yourselves. Well, the probability that for a given signal that arrives at this particular node, right, the probability that I keep on propagating this activity will be p times z minus 1. Why z minus 1? Because I've used this link to get the activity to me. So this link is already used. And now I only have 2 links out of the total number of z links in order to keep on propagating this, whatever activity processes. Could be, for example, a virus that it's propagating in a population, that it's structured in this case in a very regular way, right? So that's the probability that I keep on producing this activity, right? And this happens at each iteration, so you can think of this as sort of a reticular wave that it moves onwards and so on. So it basically will happen for all the active nodes at time t minus 1, right? Because this is an iterative process, very quickly we can spot something that we have already resolved for our issue, for our quasi-species problem, right? In this case, if we look at this, we know that a at time t, it will be equal to some value times a at time t minus 1. So how could we make this signal, the activity signal, decay over time? Well, the only way that this happens is if this is less than 1, then activity decays. Whereas if this is larger than 1, activity grows, right? Because I would be multiplying a value by something that is larger than 1 and keep doing so. As a matter of fact, this defines a percolation threshold, that it's basically what happens when this exactly equals 1, and it's, if you see, when this exactly equals 1, p sub c, this is the critical percolation point, is going to be 1 over z minus 1, right? And basically you could say, as we have already said, that if p is larger than p sub c, then basically the activity will grow exponentially with some value, and then if p is less than p sub c, the activity will decay with some alpha prime. Okay? And the interesting part is that sometimes when we look at also evolutionary dynamical systems, which biology is the major example for this, we find that some of these systems, they also poise themselves at this critical percolation threshold, right? So this is a very beautiful example that you can think about it at home. It basically, what we have done with the quasi-species problem is extrapolate from these ideas and go into solving the exact same problem that we solved before, with all the major implications that we've mentioned regarding the prediction that you can make, for example, for RNA viruses, and how they are poised at the critical mutation rate or mutation probability. But then this is a very interesting way of looking at the same problem from a completely different optics and yet getting the same result.